Welcome everyone. The Society of Petroleum Engineers Drilling Systems Automation Technical Section is pleased to present this virtual seminar, From Data to Actions, Improving the Value of Drilling Data in Operations, Engineering, and Research. My name is Jennifer and I'm the facilitator. Note that this call is being recorded and all lines are muted. If you're listening over your phone and need help, press *0. And if you have any other difficulties, you can send us a message right there in the chat box or email spe@compartners.com. The presentation will last up to 90 minutes and does include a question and answer period at the end. However, please feel free to queue up your questions for us at any point. To do so, simply type them into the chat box in the lower left corner of your screen and then be sure to click on the send button. There is a poll question in the presentation, and when that poll question appears, just click in the box next to your answer choice, and all polling is anonymous. Now I'm pleased to welcome our moderator. Robin McMillan attained a degree in geology from the University of Leeds in England and started his oilfield career over 35 years ago on drilling rigs in South Texas. Since then, Robin has worked in many countries, including 8 years in Latin America. Having joined the drill bit company ReedHycalog in 1991, Robin worked in several sales and management positions, including the management of Schlumberger Drilling and Measurements in Canada. Robin was appointed as president of ReedHycalog in 2008, and his current position is Senior Vice President for Business Development at National Oilwell Varco. Robin has published technical papers on drilling automation, drill bit design, and managed pressure drilling, and holds a patent on drill bit design. He is chairman of the International Association of Drilling Contractors Advanced Rig Technology Committee. He moderates these technical webinars for SPE and is a member of the International Society of Automation. Robin, welcome. I'll go ahead and turn it over to you.
Great. Thank you, Jennifer. Good morning, everyone. Before we get started, I'd just like to thank the SPE Foundation for sponsoring this web event. Now it's my pleasure to introduce our speaker today, who is Teresa Baumgartner, and she is a PhD candidate at the Petroleum Engineering Department in the University of Texas at Austin. Teresa holds 2 master's degrees in drilling engineering and business administration, as well as a bachelor degree in petroleum engineering, all from the University of Leoben in Austria, where Teresa grew up. She has gained practical experience in management consulting and numerous projects and internships with oil and gas companies across the globe. Teresa joined the Drilling Automation Research Group at UT Austin in 2013. In her PhD research, Teresa is working on the interpretation, automatic analysis, and modeling of data from downhole sensors. She is applying pattern recognition and other machine learning techniques to these data sets that are considered the largest and yet most unexplored in the petroleum engineering area. So welcome, Teresa, and over to you.
Thank you, Robin. So as Robin already mentioned, I'm a PhD candidate at the University of Texas in Austin, hopefully only for 2 more days, because I'll defend my dissertation this Friday. And we're working on various aspects around drilling automation, including research on data. And data has been given increasing attention, also amongst the SPE research community. I, and probably many of you, attended the workshop, the Great Drilling Automation Debate in Houston last week. And there were lots of great talks and great debates, but a lot of the participants were technical managers or above. And so in this webinar today, I want to share with you aspects of data from somebody who works with drilling data, actually lots of drilling data, every single day. And I try to point out things that may seem very easy in theory and as a concept, but are really big problems in practice. I also want to emphasize that whatever we as an industry need to do in order to allow data to fulfill all these big hopes and dreams that we kind of impose on it. So the agenda for today, I'll have an extended introduction. When we talk about data interpretation, which is still a big issue, we talk about data requirements. I'll give you some examples of data applications that we work and develop at UT, and I'll talk about data structures and metadata. So I just want to give you a little bit of context how we work with data at UT Austin. And what you see here in this picture is our real-time operating center. It's in the basement of the Petroleum Engineering Department. Here we either stream data or get it in the form of memory data, so historic data from multiple different operators and service providers. So we have all the usual software that companies probably have as well. But since we do research and like to innovate, we use software that allows us a little bit more flexibility in manipulating data or just displaying it however we want. So usually we use MATLAB, R, Spotfire, and sometimes Excel as well. And I myself work with a lot of high-frequency data, and I don't think any of these standard softwares are equipped to displaying that. We have multiple data projects, including research on downhole data, project positioning, tortuosity, directional drilling, performance evaluation, and research on data structures and data standards. Eric van Oort is our supervisor, just like Pradeep Ashok as well. Myself and 3 other PhD students are working in this field, and we every semester have at least 10 undergrad students that help us with data and get trained on data analysis as well. And we have huge support from the industry that doesn't only give us data, but they also give us advice and feedback and tell us about their problems. So there's always this debate what comes first. Do we just automate what we already do and maybe re-engineer later, or do we have to perfectly optimize our processes before we can even think about automation? So I think it's a bit of both. And most importantly, it's really not a decision for us to make because it almost comes naturally. And why? Because we, anyways, cannot just automate. So in order to automate, we need controls. But controls are governed by algorithms and equations. And those algorithms can really only be developed if we have procedures in place. So it all starts with having the right data measurements to understand and develop such procedures in the first place. And so we need to acknowledge that drilling is a science that is governed by physics to even start developing consistent procedures that are then turned into equations, that turn into control and automation. And what we at UT and probably elsewhere realize that if we have this long-term goal of drilling automation, in order to get there, we first need to truly understand the science behind drilling. And that will be almost automatically truly optimized because we question the data and the knowledge that we already have and learn more by doing it. And so we can truly optimize by just knowing a lot about the drilling process, much more than we used to. And so this long-term goal of drilling automation, at least anyways, leads to the short-term successes of optimizing whatever we do in terms of procedures. So it's very comparable to how safety cultures in organizations not only lead to less incidents, but they also can improve performances overall. Because to truly make a process safe, it has to be understood and documented and carried out in a consistent way. So we believe in automation, but also it will help us to optimize and have value there. Another topic I'd like to take up kind of from the workshop last week is this artificial intelligence and how it can apply to our industry. I did get a little bit of a sentiment from the talks during the workshop that AI or machine learning or big data or data mining or however you want to call it, it's out there and it has helped so many other industries. And it's just going to come one day and kind of magically solve our problems. And especially when it comes to things like data quality and data structures. So I think people think, so we don't have to really worry about it. It's just going to, be solved one day. It's fine. But from our perspective, so we do think AI holds incredible opportunities, but there are just no free lunches. Also in every other industry, data creation and data analysis and get the data structure right takes at least 80%, 90%. In our industry, it's probably more like 90 or 95% of the effort, but just no one ever talks about it. And I would say there will be no magic, so we can harvest the benefits of AI, but we do have to work hard and prepare our data for such applications first. It's not just gonna naturally come to us. So to support what I just said, I want to say that we do have a lot of data, but we but I wouldn't call it big data. It's rather called metadata. For instance, we do have a lot of contextual information, like things we find in a data-driven report. So here there's problems with the top drives, and there's a lot of typos there. So it's hard for machine learning systems to recognize that. Same as weight on weather. It's really important to know that, because if we just feed this into an algorithm, there's no way we can find out what the context of the operation was. And these problems can be solved, so we can have natural language processing, for instance, that gets rid of the typos and classifies these words and kind of knows what it's doing. And I've actually done this in an internship project, but we just need to actually get to work and do it. So I would say one well, it's a lot of data, but really it's not big data. Big data might be 100 wells that we can put together and compare and create data sets. But all these data sets need to contain data that is comprehensive, complete, comparable, and categorized. And I would even add, corrected or calibrated to that. And then we can start talking about big data applications, not just in the way that we do it right now. So I really want you to take away from this talk that there's just no artificial intelligence magic. And to support that point, I want to give you a quick example from another industry. This example is very basic, but it shows what artificial intelligence or data mining actually does, and how we need to prepare our data in order to do that. The medical industry was probably one of the first ones that followed this route of data mining, at least for their research purposes. So for instance, if we want to diagnose diabetes in a patient without taking an expensive blood test, for instance, we can see that there are other indicators in the data about the patient that have already been collected before. And so we indirectly diagnose diabetes. It's kind of like judging a person based on superficial qualities about things we really cannot know about. In this example, we apply a classification. So the patient has diabetes, yes or no, using supervised learning. That means that we show the algorithm examples of patients where we already know that the outcome is diabetes, yes or no, and then train this algorithm based on these results that we feed it in. So the other form would be unsupervised learning, where we just feed the data to the algorithm but don't tell it the classifications that can come up with it itself, but that's more difficult. So a typical data set for something like this has a lot of patients. Each patient is a row, and it can have tens of thousands of rows. We have features. Each feature describes the patient. So the patient has a body mass index, it has blood pressure, it has a waist size, and these are continuous variables. The patient doesn't smoke, or smokes a lot, or smokes only sometimes, and it's kind of a class. The patient can have binary features, so yes or no, for instance, is the patient female or male? And because there are so many patients, if certain data is not available, we probably usually just throw the entire row out and just not use it. If that's not an option because we don't have too many patients, we can make up for this missing value by applying certain other techniques to it. So it's important to have a complete data set. You can see already that the body mass index is a feature that is universally standardized for all patients, not like our, for instance, vibrations, or also probably in our case, we would have a data set that has 5 different units to it. So this is very clean, standardized. All outliers are removed, and physically impossible values are removed as well. And so now we can feed this to our algorithm to train it. And the algorithm can be anything like, for instance, a neural net, a Bayesian classifier, logistic regression, etc., just to kind of use these terms that neural net isn't that special. We split this entire set into some data that we train the algorithm with, and then some data that we test the algorithm with. So the test data doesn't have the diagnosis, and we compare the outcome of the algorithm with the actual diagnosis that exists already. In a 2D case, so we only have 2D features, it's easy to explain. If you look at the graph on the right right lower corner. So the y-axis is the fitness of the patient, and the x-axis is the age, just a made-up example. If the patient is old and fit, it won't have the disease. If he's unfit and young, he'll probably have it. If he's unfit and old, he most likely has it. So in this simple 2D case, it's easy to see. And now imagine the same thing with not 2 features, but 100 features. And this is just what this data mining example actually does. The algorithm can also find out which features are important and which ones are not for the outcome, so we can remove irrelevant things and don't have to measure that for this particular outcome. Can we do something similar in drilling? The answer is yes, probably. In drilling, one of the most obvious and at the earliest applications of such a thing could be ROP optimization, based on the premise that there is kind of a perfect combination of RPM and weight on bit. And that's what you see in the graph as well. So if we find this perfect ROP point, we want to stay there and keep the parameters and drill with an optimized ROP until the boundary conditions change. And what are some of the barriers in our area? So yes, we do have lots of data, but our data is time series data, most of it. So it doesn't quite describe our patient. So for instance, in the medical world, if I had a patient and I knew what this patient ate for the last 4 years, I'd first need to extract relevant features. For instance, what was the average sugar consumption of that patient? And that might be relevant for the diagnosis of diabetes, but not everything the patient ate, and I cannot really feed that into the algorithm. Same with drilling. So first, all important factors need to be captured as quote-unquote features. For instance, the stabilizer placement. So how should the precision of the stabilizer be categorized into something that the machine can capture? Also, not all the features that are relevant can be actually captured. So sometimes we don't yet have sensors, like what's the human impact, for instance. The other problem is that we don't have actually too much data, so data is sparse. In order to create that heat map from purely data, we have to have lots of combinations of RPM and weight on bit. This corresponds to a specific ROP. So basically for each style on the map, you need that combination. But this problem is that the map changes for each formation. It changes for each different BHA design, for different bits, for different depths, for different rigs, etc. And adding that all together, there's simply not enough data for that. And because it's still really hard to combine, in our field, data from thousands of wells, we don't have enough data to properly do such applications yet. So there might be other ways to get around it, like using physics and having other smart algorithms to combine it. But it's just not that easy yet. And back to my point of AI or machine learning requiring proper data structures to be applicable. So some of you might say, well, but there will be an algorithm that one day can just do it all and, sort through my data and just doesn't need me to do it manually. But I want to give you an example from a company that's probably, that has probably employed the smartest and best AI researchers from this planet in the last couple of years. So this is not very well known, and the source is kind of insider information from someone who works with this Google shopping product. So the idea is if you search for something like a hairdryer online, you will find offers from stores close to you, and it displays the prices that are updated in real time. All these companies that are shown here are, of course, Google's clients. They have contracts with them, pay them money to do so. And Google just doesn't find these real-time prices online either with their super smart algorithm. The clients have to build websites in very specific ways, and they have to add tags to the field that are very well specified and that show the prices and tell the Google algorithms like, hey, here, this is the price that you have to display. In addition, Google can't do it all automatically, so they have data centers in India and probably some other places where thousands of people manually sort through the data and classify and quality check it. For instance, they classify if a product is a weapon that Google is not allowed to sell, and so people have to actually go and do a good job because algorithms cannot yet. So I'd argue if not even Google has this kind of magic right now, we probably as an industry won't have that soon either. So we better get to do our work. I'd say it's really all about baby steps. So I hope we can show the possibilities that AI has to offer by solving small and standalone problems. And those small problems probably need the right data structures, and the data needs to meet certain criteria. So we define them and fulfill the criteria for a particular application. But by doing that, we open up for more solutions, for more problems probably as well, etc. And this is kind of a continuous improvement process. So we start somewhere small and then actually get the bigger picture later on. And so today's talk is about some of these current problems that we have and we're trying to solve at UT. And the problems revolve around data interpretation, requirements for sample rates or other things, data formats, and then some simple data correction algorithms. To wake you up, I have a quick polling question, and I want to give your opinion. So who should own big data and drilling data? So by this I mean data that is valuable for the drilling process and not like just some temperature of a machine that's pretty unrelated. So please go ahead and click now. Okay, some opinions are coming in. So seems like the operator is in favor right now. Different owners for different data at the same time. Okay, we still have some people voting. No one likes the idea of a third party. Okay, any more clicks? Yes, here's one more. Okay, thank you very much. So, since we continue, I'm going to comment on this at a later point. There is one more topic I want to follow up on from the workshop, and that topic is data aggregation. And data aggregation could have two meanings. One is just to merge data from various sources together into a big data historian, for instance. And the other one is reducing the volumes of data into something that is more manageable and handleable. In the workshop, data aggregation was used as just one concept and one step of many. And I want to point out that it's one of those things that is really easy in theory, but in practice, it can make or break the system if it's not done correctly. This is an example of downhole data and aggregation, how we currently do it. So a downhole sensor can have sample rates of hundreds or thousands of hertz. And of course, that's way too much to handle, and so we want to aggregate it. And so the way it is currently done is that we just capture statistics, so the minimum and maximum value, an average value, or maybe a standard deviation over a particular time window of maybe, say, 5 seconds or 10 seconds. And then we discard the actual data and measurement. And as you can see here already, so those statistics don't really describe what is going on there all that well. In this case, it's a bad form as well, but if we only have the statistics, we don't really know too much about that. So the theory behind data aggregation